Hello, my name is Nate Allwine, and I am the project lead for the Aerospace Rocketry Committee at Western Michigan University. Our club organization is laid out here with me as the team lead overseeing team operations, Alexis Lind as the launch vehicle lead managing simulation and design of our rocket, along with launch planning, recovery, and construction of our vehicle. We also have Jonathan Wine as our payload team lead, managing the design, construction, and the testing for our payload. Additionally, our faculty advisor is Dr. Christina Lemmer. The sub-team leads will now provide some details into their systems.
Hello, my name is Jonathan Wine. I'm the leader of the Western Michigan University 2022 Rocketry Payload Team. Here's a list of all of my teammates. Getting right into the design, you can see we decided to pursue a multi-rotor drone this year. This was chosen for its ability to fly against the wind, as well as the low amount of space taken within the rocket. The two images shown are models of the payload system in its collapsed position on the left. This is how it will be stowed in the rocket, and its open position on the right. These models use simple representations of each part, which are scaled correctly to ensure that the drone will fit in the rocket in real life. Using the image on the left and starting at the top, the blue rectangular prism represents our GPS. The four black rectangles represent pieces of fiberglass that will be used to mount our electronics. On the second rectangle down, we will have our telemetry and Arduino. And the amber rectangular prism on the third black rectangle represents our flight controller and ESC. Below that is our system of pivots that allow the drone to collapse, followed by four fiberglass arms, which support the motor mounts, motors, and propellers. The gray cylinder in the center represents a string that will connect to the battery box, which is the yellow rectangular prism at the very base. This battery box will house both our battery and the payload golf ball. As far as aerodynamics go, we have a 9.5-inch X frame. This means that there's 9.5 inches from motor to motor across the center of the drone. The propellers we'll use will be 5-inch diameter two-blade propellers with 3.5 inches of pitch. These are represented by the pink rectangular prisms in the models. The two-blade propellers were chosen both for their efficiency and their ability to fit within the rocket. The all-up weight of our drone will be 850 grams. For power and propulsion, we will have an 1850 milliamp hour 6S battery. This will be connected to our Teco 32 4-in-1 electronic speed controller, which will then connect to four Zing 2 2604 1350 kV motors. These motors are represented by the blue cylinders in the models. And these motors were also chosen for their efficiency and the extended flight time of a low kV. This image shows a top-down view of the drone, and the yellow circle around it represents the inner diameter of the rocket. This shows that the drone will be able to fit inside of the rocket before deployment. For the rest of our electronics, we have a Holybro Kakute F7 flight controller with an MPU 6000 gyroscope, and this will be loaded with iNav firmware. This firmware will use the Bayesian BN880 GPS with integrated compass to run a waypoint mission and return us to the target. Each waypoint will be programmed with a specific altitude, and this is how we'll control our descent velocity below 300 feet above ground level. The transmitter we'll use is an FrSky Access Archer M+ mini receiver, and this will transmit telemetry data back to our ground control station, as well as controls to the drone if necessary. We will also use an Arduino Nano and MPL I2C barometer to determine the altitude of the drone. Here's an image of our drone in flight. You can see that this drone looks very different from the models shown previously. This is because this is actually a test frame, so that we can test out the waypoint missions without worrying about breaking the final parts needed for the drone.
Hi, my name is Alexis Lind. I'm the launch vehicle team lead at Western Michigan University for the Rocketry Club. Our launch vehicle members are listed below. This year we went with a fiberglass 4-inch diameter Frenzy XL design. Here we have the open rocket drawing at the top and the paint design at the bottom. We will have a stability of 1.78 calibers, a CG of 166 centimeters, and a CP of 184 centimeters. This year we will be ejecting at our payload and our parachute at two different sections of the rocket, so we will have two different ejection charges. The first stage of the rocket will contain the motor and the parachute. It will separate at the bottom of the avionics using black powder. The second stage will separate at the nose cone and the second section above the avionics, again using black powder. Both ejection charges will be a result of the apogee setting on an Easy Mini altimeters. We will be using two for both charges. Here are some pictures of construction. We are painting on the left, and we are sanding down our motor tube, or our center rings on our motor tube on the right. Here's a launch simulation that we ran through OpenRocket. Our motor has a 14-second delay and hits just above 9,000 feet for our apogee, which is within the 8,000 feet mission requirements. Here's our thrust curve. Our motor we are using is the Aerotech L2200G motor with a 14-second delay. Thank you for watching, and see you in April.